So it's my great honor to introduce our second speaker, which will be delivered by Professor Gustavo Duque. Professor Duque is the chair in geriatric medicine and director of Luis in McGill Center of Excellency in Sustainable Health for Seniors at McGill University in Canada. Today we are privileged to have him give a lecture entitled Geroscience's approach to the development of biomarkers for age-related diseases. Actually, in aging society, achieving healthy aging has been always a key goal. But it's not just about living longer. It's about slowing down the effect of aging on our bodies and keep things working smoothly as we get older. So the Geroscience's approach focuses on slowing down the aging process itself and could help to prevent or delay many different age-related diseases at the same time. So ladies and gentlemen, please join me to welcome Professor Duque.
Thank you very much, Mr. Chair, for the nice introduction. It's a pleasure to be here in Taiwan. I love coming here. When I received this kind invitation, I was very happy because this is a great opportunity to have a very solid scientific exchange, but at the same time to catch up with very good friends not only from here, from Taiwan, but also from all over Asia. So today we're going to talk a little bit about the geroscience approach and how we understand the development of biomarkers from the geroscience perspective. And I'm sure that you are familiar with the way of how biomarkers are validated and developed. You know that there is first the biomarker discovery, which involves the biological demonstration that there is an association between a disease or several diseases and a biological phenomenon. And this is demonstrated, and here you can see some of the challenges that people find to do that, and we find that in the lab is demonstrated usually by animal models or biological samples, and then we have to go into the analytical validation, which goes into groups that may have the disease or may have the condition or several conditions, and we can demonstrate that there is the presence of the biomarker is there. There are biomarkers that we can demonstrate are indicators of good health, and other biomarkers that are indicators of predictors of adverse outcomes and disease. And then the clinical validation, which usually we do through cohorts, and the previous presentation was a clear example of how we identify these biomarkers in this kind of cohorts, and then the regulatory qualification, approval, and use in practice. What I'm going to show today, and I'm going to share some of the studies that we have done so far at McGill, and when I was in Melbourne and in Australia before, most of these biomarkers have reached the point of clinical validation. So I didn't want to bring biomarkers that are already established in clinical practice, because I think that for the purposes of this conference, I think that I would like to share with you the new upcoming biomarkers. And for those of you who are not familiar with the concept of geroscience, this is becoming a hot topic now in geriatric medicine. The concept is relatively simple, is that through geroscience, we look at different mechanisms, biological mechanisms, that are shared by several age-related conditions. So we don't look and from the geroscience perspective, we don't look at separate entities, separate diseases, and try to look at biomarkers for that separate disease or therapies for the separate diseases. We try to identify through the biological components, we try to identify treatments and of course biomarkers that will facilitate the interventions that target several conditions at the same time. It's cost effective, and we think that is probably the future of geriatric medicine. And geroscience, the concept of geroscience goes around these, what we call the hallmarks of aging. So you can see, initially there were 6, now there were like 8, and now I think there are 12, and hopefully we're not going to increase it more, because then we will have to, will make the Geroscience field very complex. But you can see some of these are, for instance, this biosis, which relates a lot of microbiome. You can see genomic instability. So I will not go into all of these, mitochondrial dysfunction, because I was looking at the program for this conference, and several of the presentations will relate to one or a few of these hallmarks of aging. What I will try to do in this 20 minutes or so, I'm going to share with you some examples of how we have approached and how we have tried to develop some biomarkers using or targeting these new hallmarks of aging. So the first one, for instance, just to give you a first example, is fat. Fat infiltration, and here the example, because my lab works a lot on muscle and bone, but this is, I brought you some examples that we understand that when fat infiltrates, and this, I'm not talking here about obesity, I'm talking here about this fat that is abnormal, that infiltrates the muscle and bone, for instance, and I will show you also a couple of examples of other organs that are infiltrated by fat. But at the same time, we know that it relates to inflammation, it relates to metabolic dysfunction, and nutrient sensing that is affected. So these are three hallmarks that we can target just by measuring fat or characterizing the fat that infiltrates the muscle and bone. And why is that important? Well, because we know that fat cells that infiltrate these organs come from the same precursor, the mesenchymal stem cell. So if the mesenchymal stem cell is affected by aging or by the disease, then we are going to have a predominant differentiation of those cells into fat. And that fat starts infiltrating the muscle, bone, and interestingly, it starts infiltrating other organs. So if we have less differentiation of stem cells into fat, let's say we have healthy bones and healthy muscle, so the presence or absence of fat in those organs will be a good indicator of healthy aging and healthy longevity. So, and this is what we see, you know, when we look at a sarcopenic muscle, this is what we see, lots of fat infiltrating not only around the muscle, but also inside the fiber. We have the same phenomenon in the bone marrow of osteoporotic bone. And what we did, trying to understand and to identify what are the consequences of this fat in these organs, and also trying to identify whether we can use fat as a biomarker for health-related conditions, because again, it has a very strong inflammatory effect. So what we did was we evaluated the fat content. We did a complete lipidomic analysis. This is in mice, in aged mice, of fat that infiltrates the muscle, fat that infiltrates the bone, and we compare it to the serum lipids. And basically what we found is that marrow and muscular fat are very similar, very toxic, and very inflammatory. That approach allowed us to identify potential components of this fat that we can in the future, and at this moment we are evaluating that in humans, we can understand and use as a biomarker for at least for 2 or 3 different age-related conditions. And because their similarities, what happened in the bone with the presence of this fat versus what happens in the muscle in the presence of the fat is very similar. It's a catabolic state, inflammatory state, lipotoxic state. As I say, we are trying to identify which are those pro-inflammatory specific factors that are present in the fat at the same time in muscle and bone that deteriorates the function of these organs and also affect other organs and in general induce systemic inflammation. But that's not the only thing we do. We also try to quantify it. It's not only to look at the composition, but we can measure it. Now we're using a software that can quantify the bone marrow fat, all the yellow components here, in any imaging, in CT scans, in MRIs. We can quantify it, and we can determine the risk of having adverse events by quantifying the fat infiltration, not only in bone, but also in muscle, just with imaging. Something that we developed also with as another way of approaching it is this is a collaboration with a group in Norway, Dag Arsland and his group. They have these longitudinal cohorts in dementia. And we say, okay, why not quantify fat infiltration in the masseters or in the tongue as a biomarker for deterioration and dementia, people with dementia, or a predictor of adverse outcomes in older persons living with dementia. And we have been able to demonstrate with high accuracy, this is a paper is in press at this moment in the Journal of Cachesis, Sarcopenia and Muscle, that just by measuring fat infiltration in the tongue and in the masseters, we are able to predict adverse outcomes in these patients. The next step now is to use and profit from artificial intelligence and deep learning. So now we have a deep learning model that we validated that can analyze around 2,000 scans per week and is able to predict all these adverse events in longitudinal cohorts. So I invite you, you have in your cohorts, you have imaging and you are interested on helping us to validate this deep learning model, you are more than welcome to contact me and collaborate. Second example, tryptophan metabolism. I will go quicker here, but we know that tryptophan is an amino acid that is essential, that is metabolized by the microbiota. So we have this biosis, the metabolism of this tryptophan will be affected. We know that in high levels of inflammation, we also have alterations. And why is that important? Why we look at tryptophan? Well, this is a very interesting example of how there is a connection between the gut and the brain, because the tryptophan is metabolized into serotonin, which is probably the better known metabolite of tryptophan, but it's also a metabolite, or mostly metabolite, through the kynurenine pathway. And what happens when we have a situation when there is bad aging, when there is a lot of inflammation, when we have dysfunctional microbiota? Well, what we have is that a lot of kynurenine is produced, and kynurenine is a terrible metabolite that is clearly associated with unhealthy aging, because it affects different components of aging. It affects stem cells. So remember that stem cells depletion, that is one of the hallmarks of aging. It also associates with chronic inflammation or inflammation. So if we have too much kynurenine, we have unhealthy aging. What we have also looked at is that tryptophan has also a good metabolite, that is the picolinic acid, one of the end metabolites. So in conditions of healthy aging, healthy microbiota, not in too much inflammation, the pathway ends up producing metabolites that are anabolic, which we have demonstrated to be anabolic in bone. I will not go into all the details. And we have been demonstrated that it's anabolic in muscle. So if we have good levels of these anti-inflammatory, antioxidant, anabolic metabolites from the tryptophan, then we can demonstrate that it has a biological impact on healthy aging. So what we have done in humans, we have evaluated more than 14 metabolites of the kynurenine pathway, and we have been able to demonstrate and to validate these metabolites as indicators or predictors of adverse outcomes, as an indicator of healthy aging. So we have, as I already mentioned, all these ratios that are anabolic. Then we have better function, mobility, and less frailty. If we have the more kynurenine type of metabolites, we have unhealthy aging, and we have more frailty. So this is another example of this kind of the use of Geroscience to identify that. The next one, again very quickly, stem cells exhaustion, which is one of the major ones that I have already mentioned before. And for this, I have done these studies with my postdoc, Jack Feehan, which, by the way, is not my son, but he's my postdoc. He did a PhD only on this kind of stem cells. We focus on these particular populations, circulating osteoprogenitors, known as COP cells. These are very interesting cells. These COP cells are in the circulation. They come from the bone marrow. Now we know that they come from the bone marrow. They are stem cells that are in the circulation, they are in our bloodstream. And we can quantify it by flow cytometry. Very simple way to do it. Why we are interested in this as an indicator of stem cell exhaustion with aging? Because we have found that low levels of COP cells are associated with osteosarcopenia, with low bone and muscle mass. We know that low levels of COP cells are associated with frailty. We already published that a while ago. So this could be an indicator, a good biomarker of healthy and unhealthy aging, particularly in the context of mobility, osteosarcopenia, and frailty. So this recent paper that we summarized, in this paper we summarize all the evidence that we have at this moment. We have already characterized these cells. We know that there are stem cells. They go down with aging, but in particular they go down mostly with unhealthy aging. And to finalize, we have the final group, or the other group of biomarkers that we are exploring from the Geroscience perspective, which is telomerase activity and epigenetic clock. So we know that there are epigenetic alterations, there is telomere alterations as well in unhealthy aging. So we are looking at this moment at two very interesting biomarkers. One of them is the Dunedin pace, which is a DNA methylation, which seems to be the best predictor of adverse outcomes. It's becoming a very hot topic at this moment. And we are, through different cohorts, very much longitudinal cohorts, we have collected data so far, including the UK Biobank and other big biobanks. We have collected data from about 1.2 million people, where we are analyzing all these biomarkers, particularly from the perspective of the DNA methylation, but also, and I will just go straight to this one, also we have just finalized this study from the UK Biobank, analyzing 20,000 participants in the UK Biobank, where we found that telomere length was positively associated with greater muscle volume in both sexes, and interestingly, is a very good indicator of healthy aging. So if we have good telomere length, definitely we have better muscle mass, mobility, independence, and less frailty. So I just wanted to share with you 4 examples of what we are doing at this moment from the Geroscience perspective. So the Geroscience approach could provide a set of robust biomarkers. If we look from this perspective of different components of hallmarks of aging, most of the methods are already there, so we don't have to create the methods. We just have to provide the samples and get the good rationale, and we can use all these longitudinal cohort studies. So with this, I would like to thank you again for the invitation, and in particular, thanks to all our collaborators around the world who have helped us to develop these studies, and of course, and thank to the people who paid the bill for all these studies. Thank you very much for your attention.
So thank you, Professor Dance, for your excellent speech covering the new potential biomarker in the aging studies. So again, please keep your question until the panel discussions.